Hello, welcome all and thank you for joining. My name is Ian Fennell, I'm the Manager of Developer Relations at Matillion. In this session I'm going to talk about the low-code, no-code approach to problem solving, focusing on a data integration context. Data integration faces the same main challenge as every other area of information technology, which is simply trying to keep up with the pace of change. But data integration does have some unique challenges of its own. I think probably the biggest two are that most design and architecture is process-oriented rather than data-oriented, and secondly that data processing functions are stateful rather than stateless. These things mean that if you intend to use low-code, no-code in a data integration project, you have to look beyond the default mindset of process orientation and statelessness. So with that in mind, in this session I'm going to try and give some guidance, examples, and things to look out for in a data-oriented low-code, no-code platform. Before diving into the content, I want to spend 30 seconds explaining my own background. It will help you understand the influences that led to this presentation. I've done a fair amount of coding and software development, starting out in fintech, coding real-time messaging software in C. Then I worked for some years in aerospace, developing OLTP systems, and I got into telemetry and spatial data. In other words, I could hardly have been any more process-oriented. It was not intentional, I just fell into that pattern by default. Especially working in middleware, messaging and object orientation, everything is almost completely stateless. Just over 20 years ago, I made a career switch into data integration. It was quite some time before I began to really appreciate how much of a profound change in mindset it is to switch to a data-oriented outlook. Since making that switch, I've worked for many years as a data warehousing consultant, and low-code, no-code platforms have been a vital enabler. Basically, they help you deliver faster and more accurately. With a low-code, no-code platform, you avoid having to do the boring stuff, the things that machines are good at, and that lets you focus where you can add most value. I'm going to split this into two main parts. Part one is more practical and hands-on with examples and patterns. Part two is a step back to look at low-code, no-code more broadly, and especially in the context of DataOps. I'll also cover some ways to go about evaluating low-code, no-code platforms. In the next two slides after this one, I'm going to talk about two great digital transformation challenges that occur when you're tackling data integration. Both of these challenges have the same root cause. When you think about it, it's actually pretty strange to even be talking about software code and data in the same breath. They're really very different things. If you're thinking about code, the data comes and goes, but it's just an input or an output. It's not important at all. And the other way around, if you're looking at some data, the code really does not matter. The data is the only important thing. A little bit tongue-in-cheek, but let me bring that to life for a moment. Imagine there's a data problem. You're looking at the data or report, and something's wrong with it. You ask around and you start to hear things like this. The software adhered 100% to the spec. All the code was written in the very latest fashionable programming language. There were no errors or warnings when the code ran. The code ran very quickly. The code ran in the cloud. Everything was fine last week. The code hasn't changed. How can it be wrong now? None of those arguments are helpful because they all relate to the code and not to the data. They're probably all true, but they're just not relevant. That is the fundamental reason why data integration is an ideal context for low-code, no-code platforms. The situation is that you need code to shift data around and to integrate it. The code is not the primary consideration. The code is not the end goal. You do need it, but only to achieve something else. This is the first of the two great digital transformation challenges that apply to data integration. You need code to work on your data, but you have to be in position to change that code rapidly and reliably. You need to be able to iterate. If you think quite broadly about a data team, there are two main subgroups. First, the reporting and analytics teams. They integrate data to make it optimal for human consumption, and they call their work data transformation. And second, the data science teams. They treat data to make it optimal for consumption by algorithms, and they call their work feature engineering. There is a lot in common with the work those two groups of roles do. In a good, highly productive data culture, those two subgroups will be working both with the end users and between themselves in a joined-up way. Here's what happens with data systems. As soon as everything is working, something changes. Either the business changes, or the source systems change, or their data processing rules get modified, or an output from the data team sparks a new question. In a healthy business, all those changes should be happening often. When sources are changing, it implies that the business is adapting to new opportunities, especially time-sensitive ones. And whenever data products are quickly prompting new questions, it's a very good sign that they're hitting the mark. So, whenever something changes, the data team has to be ready to issue software changes in short release cycles. It is so important to embrace this and see it as an opportunity. A data team that can do that quickly and reliably can be a real differentiator. And a key enabler for making software changes quickly and reliably is, of course, low-code, no-code. Now on to the second of the two great digital transformation challenges that apply to data integration. This is that data has state. You tend to hit this as soon as you start iterating rapidly. Most of the work to create data processing logic involves figuring out how it should interact with the underlying data. It's what we call the state. The way the code reads and writes data depends very heavily on the structures and on the values in the data. So the design of a data processing function is tightly coupled to the schema. As soon as the schema changes, you're going to have to look again at all the data processing functions. What happens over time is that changes accumulate. The data usually ends up looking something like rock strata. Over a long time frame, the original software has probably either vanished or changed unrecognizably, but the data is still there. The data keeps a historical record of the processes that were active at the time it was collected. If you're using the front-end app that manages the data, you might not even be able to see some of it in the end. The historical data stays there, and it's lying in wait to make a surprise appearance when a data processing function attempts to use it. By the way, this is one of the main causes of the myth that source data quality is poor. Source data quality is just fine. The source data is being used right now to run the business. It's just that the rules changed and the data got left behind. Once again, you only start to find these things once you start to iterate. Both of the data team subgroups that I mentioned in the previous slide are sharing the same data, so their work is very closely interrelated. Design changes are almost certain to cascade from one team to another. That's another reason that all these data teams need to be able to iterate quickly. Low-code, no-code in a data integration context is fairly easy to explain. You should find a graphical UI with some kind of drag-and-drop interface, look for a variety of helpers in there that speed up repetitive tasks, and a low-code, no-code platform generates code that interacts with data. And in a modern context, that is going to be held in a cloud data warehouse and using a processing technique that is optimal for data, which is ELT. You will usually be able to see the code, but you don't have to write it. Now, when you're doing data integration, there are the same three choices that apply to every part of IT. You can build, buy, or outsource. Hand coding gives you absolutely top flexibility and the opportunity to create something completely unique. But to hand code, a professional software developer has to understand what needs to be done and has to know how to code that in a programming language. Now, knowing how to use any programming language is a high barrier to entry. Even more difficult to maintain somebody else's programming work or to program in an easily maintainable way in the first place. So the aim of low-code, no-code is to remove that barrier, to get the same benefits of hand coding, but without the need to be a software development expert too. I'm going to show a few practical examples in the next 3 slides. The first example I will use is to do with data pipelining. Data pipelining, or co-location, is usually the first thing you have to do when you're trying to integrate data. You have to get hold of the data before you can start to look at integrating it. There are plenty more tasks after that, of course, but I'll talk about those in the slides after this. So the first problem is getting hold of the data. Process-oriented application developers usually don't make it easy to get the data out of their app or their database. I don't think it's sinister or malicious at all, it's just a lack of understanding. Why on earth would anybody want to take their data out of this app? Look at all the fantastic processes it has. But the reality is we do need to get the data out so we can integrate it with the other 1,399 applications that the business is using, each of which are thinking along similar lines. So that's what a low-code, no-code tool has to help you with in data pipelining, getting the data out. The same applies whether it's physical co-location or virtualization. In fact, ideally, you shouldn't even have to care which approach it's taking. It should just figure out which of those options is going to work best. Those kinds of decisions are examples of boring but necessary practicalities that machines are good at. Data co-location methods like change data capture and high watermark loading have not changed for probably 50 years. You really should not be hand coding pipelines like that. It's a classic no-code or code optional area. So in general, the interfaces for low-code tools tend to be very declarative and very simple. The main aspect is usually dialogues with lists of properties like how do you connect to the source, what tables do you want, what's the primary key, how often do you want it to run, who should have access to the copied data. In summary, expect the simplest of dialogues with lots of property lists to fill in. As long as you're stuck in a completely process-oriented mindset, there is no difference between data co-location and data integration. So co-location is the end of the story. And by the way, that is the root cause why data lakes actually usually turn out to be data swamps in reality. But if you've moved beyond that into a data-oriented mindset, you'll know that after co-location comes transformation and integration. This slide is a full end-to-end illustration of a data transformation and integration process. You can see straight away there's a lot going on in this diagram. The data pipelining part I was talking about in the previous slide is the single extract and load arrow right at the top. You can see multiple tiers of data being used, and this is typical of the logical structure that will help keep the complexity under control. Inside each of those tiers, you need to think about the data model, which might be data vault or star schema or third normal form. And when you're managing data in these ways, there are common patterns once again. A filter is always just a filter, regardless of the business domain. A lookup is always just a lookup. Once again, it's the same in finance, in aerospace, in life sciences. But because every company's data is different, and in a healthy data culture, the business rules keep evolving, it often requires some human input to explain exactly how the filter should work, or exactly what to look up. So the productivity tools in this area tend to be low-code rather than no-code. A low-code tool creates a framework. You can usually see the generated code, and you'll have the opportunity to inject fragments of logic. The tool makes sure your work gets added in the right place. If anyone has ever tried to debug or maintain a SQL statement thousands of lines long, it's really difficult. Even if it was originally your work, you might literally have to spend a whole day figuring out exactly where to make one tiny modification without breaking the rest of it. In data integration, the data tends to flow from layer to layer. So the look and feel of a low-code data integration tool tends to mirror that. Most commonly, there's a drag and drop interface where you can design and build up the data flows, and some kind of data sampling where you can check if it's working or not. Blended in with that interface, you should find places where you can add your customized logic, maybe SQL fragments, for example. In the previous slide, I was talking about filters and lookups. Those are common examples of universal utility functions that you would probably find in most data transformations. But there's no need to stop there. You might find that you have a piece of bespoke functionality that's unique to your organization or your way of working, and you can take advantage of it over and over again in many different places. So look out for two other things in a low-code platform. First, a way to create your own templates made up of parameterized blocks and repeatable patterns. And second, a community exchange or marketplace where you can open source or even monetize functions that are potentially valuable to other businesses too. Sometimes a repeatable function might have quite a sophisticated interface, for example with cascading prompts. For those situations, the tool itself should offer dialogues to match the inputs. A widely used example is in file handling, where a no-code tool can detect columns in a file and turn them into a database table. You really should not be having to type out long lists of column names and data types and positions. Another common example is with semi-structured data handling. It can be really difficult to pick out a pattern just by eye, especially from a large semi-structured data sample. But that's often quite easy for a machine. So a low-code interface with this purpose should guide you through and make intelligent suggestions based on its examination of the data. On to the last section of part 1 now. I'm going to spend a few minutes to look a little more generally at some of the data-oriented patterns that work well with low-code, no-code in data integration situations. 3 patterns I'm going to focus on are on screen here, and I'll dig into each one over the next 3 slides. The first pattern is to use multiple modular small components to build up functionality, to build up sophistication, in a way that's easy to understand and maintain. I have on the screen a classic example from the world of SQL data transformation. On the left, there's a SQL function known as a window or sometimes an analytic function. It can compare rows against each other in a single operation. Next to that, there's a filter function. If you've ever looked at a piece of SQL, the filter just means the where clause. When you use those 2 components one after the other, they can work as a deduplicator. The window function can check if a row is the same as any others, and the filter can remove any rows where that is the case. The beauty of it is that both the rank and the filter components are independently very simple, easy to understand, and easy to maintain. They can also be used in many other different ways. They have this extra ability to deduplicate when you use them together in combination. And once again, deduplication is the same in life sciences, as in finance, as in aerospace, meaning that the lowest level components like this are entirely transportable. This is an example of something that you might package up into a higher level block, perhaps with some customized error handling. The second pattern is all about reducing tasks that are labor intensive and error prone. As a human operator, you really should not be doing those things yourself. Machines are good at that stuff, let them do it. On screen is an example of an unstructured source data file. In fact, it's only the first 160 bytes in the file, and the whole thing goes on for thousands more lines. To the human eye, it's not obvious at all what the file contains, but on the other hand, to a computer, would be able to quickly work out that it's an audio file and would be able to extract the data points. If you tried to do that same task manually, it would take a very long time and you would almost inevitably end up making a mistake. The human operator is trying to generate insights, certainly doesn't want to be wasting time on low-level tasks like this. Another way of thinking about this pattern is to place value on human developer time rather than on machine time. There are lots of other examples of this kind of thing. Multiple small automations, such as autofill and a data viewer I talked about earlier, can add up to great time savings. This third pattern is especially resonant with data-oriented development. In the data world, there are a lot of imperative distractions, like wait for something, run this, grant that. Declarative thinking means I don't want to have to describe all the details of how and when to do it, just make sure it ends up like the design. On screen, there's a database query, the sort of thing you might run in a transformation task, for example. The box at the top is the query expressed in imperative syntax, and the box below it is the same thing expressed in a declarative way, in other words, just as SQL. There is a reason, after all, why SQL, which is a 4GL declarative language, is used so widely in the data world. In a declarative interface, you define the goal and the machine works out the steps to make it happen. There may be a lot of steps, but the declarative pattern is much more compact because you don't have to exhaustively list every single step along the way. There are plenty of other declarative design patterns too. If anybody has ever used a REST API helper in a low-code, no-code tool, for example, you declare how it authenticates and pages, and it deals with the imperatives like connecting to the API, parsing the response, checking the TLS certificates, finding the link header, requesting the next page, etc., etc. Lots of code being generated for you and all running behind the scenes. So far, in part 1, I have been quite hands-on and specific. So now, switching into part 2, I'd like to step back a little and talk about evaluating low-code, no-code tools and where they fit into DataOps. This slide is a simple analogy for data integration. You have to get hold of all the source ingredients, which is the extract and load. Then you have to integrate them to deliver something joined up and useful. So that's the first thing to think about when you're evaluating a low-code, no-code data integration platform. Can a data-savvy business user create something end-to-end that delivers value? They should be able to do that fairly quickly, deliver a minimum viable product. You can always optimize it and productionize it later if you decide to go ahead with the platform after the evaluation. And that brings me on neatly to the second factor that comes into play. As we know, nothing ever stands still for long, so you should then evaluate whether a different data-savvy business user can maintain the solution that someone else created using the platform. The last thing on this slide is that it's also an example of the building up sophistication pattern. The extraction, loading, and transformation steps can all be managed independently. So that means ideally you're looking for a platform containing multiple tools. There is a reason for this. The main trade-off with individual low-code, no-code tools is that as they become simpler to use, the functionality becomes less flexible. With low-code, there is always the option to hand code beyond the boundaries of what the tool was designed to do. But there is a cutoff point where, rather than doing that, it just becomes much easier to use a portfolio of low-code, no-code tools within a larger platform. When you're looking at a low-code, no-code platform, there's quite a simple way to assess how much is declarative versus imperative. The trick is to think about how many distractions there are in the user interface. Let me give you an example. This always drives me crazy. If I'm trying to drop a table and there's an error message that the table doesn't exist, That's such a process-oriented imperative viewpoint. It's telling me that the process of dropping the table failed. In contrast, from a data-oriented perspective, it's much simpler. I don't want the table to exist. It's not there anyway, so that's just fine. A data-oriented mindset is a declarative mindset. In data transformation and integration, the most important thing is thinking first about how the data should end up. How it gets there is of secondary importance. Of course, the software that shuffles the data around has a vital job to do, but all those imperative concerns about when to run what, those are best managed by the computers themselves. A good DataOps example is the ability to design in a declarative way that handles schema drift. You should not have to stoop to give column-level instructions. You should only have to say, make a copy. Another DataOps example is that when you're in declarative mode, you should not need to remember to run the code at the appropriate moment in the correct order. Those are problems that machines are good at solving. This is the main way that declarative design modes make deploying solutions simpler. Virtualization is another good example of declarative thinking. When you declare a view, the machine takes care of updating it. There are no imperative timing considerations. It just happens. Another example would be a platform that lets you declare a governed and hosted API that consumers can pull from. That would mean goodbye to the majority of problems concerning timing and permissions. Thank you so much for watching. I'll give a little summary here at the end of the presentation. The main thing is that low-code, no-code is certainly not the end of software development. I think rather it's an expression of just how important software is in a data integration context. For professional software developers, low-code, no-code means having to spend less time on mundane activities and more time delivering value with your unique skills. For business users, low-code, no-code means being able to directly deploy your unique domain knowledge as a working solution.